Okay, so now we come to the properties of Poisson distribution, okay, and we show the PMF up here for you. Okay, so we will use this actually throughout for this video whenever we're trying to show certain properties of Poisson distribution. Okay, so the first property is that it's valid or well-defined, meaning that if I'm summing up all of the PMF, okay, they should be 1. And in particular, I would just highlight here that we are doing an infinite sum, okay, because as we recall, the range of the random variable x, if x follows a Poisson distribution, takes value 0, 1, 2, up to infinity, all of the possible integers. Okay, so we're doing infinite sum over here. At first glance, I guess it might be a little bit complicated and daunting to do. But this, as we show you down here, that the Taylor series from Cal 2 or AP Calculus BC, if you took that, or Math 127 here at Master, the Taylor series will be really useful for us in this case to show the well-defined property of Poisson, and in particular, this result. Okay, so this is pretty handy, so I will highlight here, and then I will ask you to keep in mind that this kind of results can be really useful for us. Okay, so lambda, e to the power of lambda is 1 plus lambda squared over 2 factorial plus lambda to the power of k over k factorial, and then you keep doing that. Okay, so we're going to use this result to show that the Poisson PMF is well defined. Okay, so the way to do it is, let's see. Okay, so we have pk. Okay, so the first thing we can do is to plug in the pk expression for Poisson. So we have e to the negative lambda k, and then k factorial. Okay. One very important technique in doing all this kind of calculation is that since the summation, okay, is about k, okay, so anything after the summation sign that is not about k is a constant in terms of the summation sign. Okay, so for us, e to the negative lambda is actually a constant, so we can bring it outside of this. Okay, so then we have this. Okay. And interestingly and importantly, if we look at this summation now, after the e to the negative lambda is outside of the summation, it's exactly e to the power of lambda. Okay, so if you look at like lambda equals to 0, this becomes 1, right? Oh, sorry, 1, yeah. And then when lambda equals to, oh, sorry, when k equals to 0, sorry about that. When k equals to 0, this is 1, okay? And when k is 1, this is lambda, so it's exactly this e to the power of lambda. So if we recognize that, we're able to do this, which is 1. Okay, so the Taylor series, okay, can be used to show that the Poisson distribution is well defined, and notice here it is required, so you need to know how to do this. Okay, so check out the textbook, I think page 136 if you want. They also show a quick proof over there. All right, so that's that. And then the second property, I mentioned it earlier in the previous video, that the mean of Poisson is actually lambda itself. Okay, so this is also required. Okay, and the textbook 137 page, that page also show a proof there. But for our video, I'm gonna show this one, so we are able to see how it works. Okay, so before we started, let's just refresh our memory that the expectation of a discrete random variable, okay, is the sum of all possible x, okay, over x times px, okay? Px is the PMF, okay? So to bring that back into the Poisson example here, we're gonna have summation. So here we're using k, right? Okay, and this is the PMF. So this again is gonna be an infinite sum. Okay, so what we do is we have k, okay, because that's x here, and e to the negative lambda, k to the lambda to the power of k, and then k factorial. Okay, so this is the starting point, okay, of how to recognize this particular the expectation. Okay, so first thing first, okay, notice that we have k here, okay, and then k factorial in the denominator. Okay, so one thing we could first recognize, okay, this will be useful, a technique that I think you have seen one of the homework exercises for previous part of chapter, I think part 2 of chapter 4. Okay, so one thing is that we can cancel out that k, so this becomes k minus 1 factorial. Okay, and also I will also, let me just add that really quick. Sorry, let me do the eraser here. Yeah, another thing, I'm going to use a different color here. Okay, another thing is that we start k from 1, and the reason is because if I look at this term, okay, when k equals to 0, that whole term is 0. Okay, so I won't have a k equals to 0 term, so pretty much I have my k starting from 1. Okay, so I delete that term of k equals to 0 from the sum first, and then I shift it, I take the canceled out the k and k factorial over here. Okay, all right, so that's a important step. Okay, and then once we do that, okay, because there's a k minus 1 factorial over here. Okay, so maybe we want to do something about this k up here as well. Okay, just because later on we might be able to cancel things by doing the Taylor series earlier. Okay, so one thing we notice is that, even though I have lambda to the power of k in the summation, so k is the thing that is being summed, right? But I can always like rewrite this as lambda. So this is lambda times lambda k minus 1. Okay, so I'm doing this again because I'm trying to match, okay, below, and then try to use the Taylor series. Okay, so if I bring my lambda to the power of k to lambda times lambda to the power of k minus 1, I have an extra copy of lambda, which is not governed by the summation, right? And also e to the negative lambda is not really governed by the summation either, because the summation is about k. So I have e to the negative lambda, okay? Also have lambda, okay? Both of these are out from my summation, because my summation is about k. Okay. All right. Okay. So the final step over here, like I said, is very similar to I think theoretical exercise from previous part, is that we can recognize that, well, if I let my k minus 1 to be I, k minus 1. Okay, so I can shift all of the terms a little bit. Okay, so I still have my e to the negative lambda times lambda. Okay, and if I let I equals to k minus 1, so what this, the whole summation now becomes, I'm just shifting a term. The I is from 0, okay, to infinity, and then I have my lambda to the power of I, and then I factorial. Okay, and this, okay, as we know from the Taylor series result from before, that this whole thing is e to the power of lambda. Okay, so that's why we got this two canceled out. So that means this canceled out, which only gives us lambda. Okay, so the expectation of Poisson random variable, okay, with parameter lambda is lambda. Okay, so again, we're seeing, so just to recap a little bit those techniques, right? We always bring whatever is not about the sum, okay, as a constant outside of the summation, okay? But more importantly here, we're trying to move things around so that we're able to use the Taylor series results that we are using earlier for showing that the PMF of Poisson is well defined or valid. Okay, so again, this is required. Okay, so please check out the textbook, page 137, if you want to go through their steps as well. Okay, and you need to know how to do this, meaning that, well, maybe in the exam or the homework, it's going to just show up that asks you to prove this is true. Okay. And the variance is also required. And I showed you earlier in those graphs that as lambda increases, the spread of the Poisson distribution also increases. Okay, so the variance turns out also to be lambda. Okay, and I won't show you here in the video, but just to recall, right, the variance of x, okay, is the expectation of x squared, right, minus the square of the expectation. Okay, so if I want to show the variance of Poisson, clearly I need to figure out what the expectation of x squared is. Okay, so the technique is very similar to what we showed earlier. Okay, and but I will just direct you to page 138 for a detailed step-by-step derivation. And I think overall it's pretty clear over there in the textbook. And notice that this is also required, so you need to know how to make it work. Okay. All right. And so with all of this in mind, let's look at a quick example here. Okay, suppose VASA students on average have 1.73 siblings. Okay, what is the probability that a randomly selected student has at most one sibling? Okay, so since, well, number of siblings is count, okay, and it's typical, we can use a Poisson distribution to describe it or to model it. And then since on average, okay, the count is 1.73. So if we think that we can use a Poisson distribution to model it, then what we are saying is that if I have my random variable x, it follows a Poisson distribution with expectation 1.73, meaning that lambda is 1.73. Okay, so we start with that, okay? And next, we know that the question is asking for the probability that randomly selected student has at most one sibling, okay? So at most one, okay, is the PMF evaluated at 0 plus the PMF evaluated at 1, okay? And then what we do down here is that, well, because we're using a Poisson to model it, okay? So we can bring in the Poisson PMF for the two values, x equals to 0 and x equals to 1, and we add them up, which is roughly about 0.48. Okay, so again, we need to recognize that we are using a Poisson distribution with lambda 1.73. So this is property. Okay, so remember, we're saying that the mean of the Poisson distribution with parameter lambda is lambda. So if the mean is 1.73, we can say that the lambda is 1.73 for a Poisson distribution. Okay, so this is a quick application, and in those exercises that we're going to do in live sessions, you're going to see variations of this. And the last property I want to cover is that sometimes, okay, Poisson distribution can be used to approximate binomial distribution. Okay, so binomial distribution, we covered it before. Okay, we use BIN, okay, N and P. Okay, so N is the number of trials, P is the success probability. Okay, so if you have a binomial random variable x, okay, if P is small, N is large, meaning that later on when you calculate lambda, which is n times p, of moderate size. Okay, so just to refresh your memory a little bit, for the binomial distribution, okay, now we know that the mean, so mu of binomials n times p. Okay, so that's why here, as you can see that, well, if the mean of the binomial distribution, which we calculate as mu n times p, okay, is moderate size, then we can use a lambda, I should say, use a Poisson distribution with the same mean to approximate it. Okay, so that's why we're writing lambda equals to n times p, because n times p itself is the mean of the binomial, and lambda we know is the mean of the Poisson. Okay, so what this is saying is that if you satisfy the conditions of that p is small, n is large, and then the mean of the binomial is of moderate size, then we can use a Poisson distribution with the same mean as the binomial distribution to approximate the binomial distribution. Okay, so graphically, I'm going to just show you over here. Okay, so the bars that you're seeing, okay, behind this, like this bars, okay, this are the a histogram, okay, showing you the counts in each bin, like 30 to 35, 35 to 40, things like that. And the height, as you can see, is density. So it's the counts divided by the total numbers. Okay, so this is, you can think of it as a PMF to some degree. Okay, and what this is showing is that we're using those bars to represent a 10,000 random draws of the binomial distribution of 1,000 n equals to 1,000, p is 0.05. Okay, so we're looking at this condition. Okay, so the histogram behind this, the bars, they're representing the binomial distribution, and the zero, like the empty circle here that we're doing in red, that's Poisson distribution with the same mean. Okay, so this is what we mean by approximation. Okay, pretty much this dotted curve that we're showing over here is giving us a good approximation of the histogram behind it. Okay, so this is helping us to visualize, okay, that if we do satisfy these conditions, we can use a Poisson distribution to approximate the binomial. Okay, so in the exercises in the live session, you will see some examples of this. The key here is that we need to meet these conditions, but also a lot of times, sometimes like say binomial distribution might be pretty hard to compute, okay, in some cases, so just so you know, and then the Poisson could be much easier to go with, okay. All right, so just to recap, we introduced the Poisson distribution. Okay, this is the PMF. Its mean is lambda, variance is lambda as well, and then you can approximate binomial distribution with small p, large N, and moderate N times P. So this is just the notation that we're doing, and then the graph earlier is to visualize that result.